Okay, so what we have here now is just going to be a quick slide that talks about the steps for conducting this Anova test, and then I'm going to go back into the document camera and go through an example. The nice thing about hypothesis testing is that the steps you follow are always the same. So the first step is going to be to write out null and alternative hypotheses. And in this case, the null and alternative hypotheses that you write are always going to be the same. The first one is that all populations that you're interested in have the same mean. And that's your null hypothesis. The alternative hypothesis is that all populations do not have the same mean. So we're going to use the test then to see if there's evidence that contradicts the idea that all the populations have exactly the same mean on some variable. The next step is to calculate a test statistic. And in this case, the test statistic that we're going to calculate is the F statistic. And the F statistic, again, describes the extent to which the groups are distinct from each other or similar to each other, and will give us evidence that can either help to disprove the null hypothesis or that can fail to disprove the null hypothesis. And we calculate the F statistic using those mean squares between groups and mean squares within groups measures that I just talked about. Finally, we decide whether to reject the null hypothesis. And we'll do this using that F distribution, where we'll see how likely it is that we would have gotten an F statistic as big or bigger than the one we got if all populations actually did have the same mean. And specifically, we'll use this information in the form of the p-value, and we will reject the null hypothesis if p is smaller than alpha as usual. And specifically, what we'll be able to state is that if all the population means were exactly the same, there would be some % chance that we would see an F statistic as extreme or more extreme than the one observed, just by chance. So in other words, if all the population means are the same, we would get the sample results that we did just by chance some percentage of the time. And if it's a small enough percentage, we will be able to conclude that the population means probably aren't the same. It's just too unlikely that we would have gotten samples that are so different from each other if the population means aren't the same. And again, we decide that it's too unlikely if we're below that alpha threshold. All right, so this is the logic of it, and now I'm going to go through an example using some actual numbers.